Shall I start?
Yes, yes, please go ahead.
Yeah. Hello and good evening, everyone. Welcome to this 125th session of Mero Eyes Eye Talks webinar powered by Mero Eye Academy. This is Ms. Solu Gautam signing in as your host for this session, and I am so glad to welcome you all for this evening. So, prior to the beginning of today's talk, I request you all to drop your queries to our live chat box that you have in between the session. So we shall discuss it later on our discussion session. So for now, I would like to move ahead to inaugurate today's session. So joining us today is our speaker, Dr. Abhishek Mandal, to share his insights on topic neural suppression mechanism during eye movements. Before he begins, let me highlight his short introduction. Dr. Abhishek has completed his PhD from Glasgow Caledonian University, and also he is the founder and CEO of the Vision Science Academy and AI startup of Ocular Interface, both based in London, UK. So, Dr. Abhishek, I welcome you to our platform on the behalf of MIRI Foundation and all our participants. Over to you, Doctor.
So thank you, Solu, for the introduction, and thank you for inviting me. It's really a pleasure to be able to speak to the audience in Nepal. I've been in Nepal long time ago, and again, it's a privilege to be back to speaking to the Nepalese audience. So today I will be talking on the neural suppression mechanism during eye movements. So what I'll do is I'll try and keep myself away from the screen, and rather than um, showing my face, I think it's more important that we can obviously go through the slides being more prominent. Okay, so what topics we'll be covering today is the visual suppression, the neural pathways, the eye movements, the visual suppression during eye movements. Some will be talking on some real life scenario, and also we will be discussing of all over the topic that we will be going through. And if you have any questions, we'll be happy to answer them. So what we understand by suppression, so it is quite a frequent term that suppression is lazy eye, like when in amblyopia, where the one of the eye gets suppressed, and what happens is there is no information like the stimuli going in the brain, and therefore the eye gradually becomes dull, or it gets suppressed and the vision deteriorates. But forget about the amblyopia suppression for now. Let's talk about how suppression can actually enhance our visual performance. Because suppression, I know this is a contrast where we are in the first point, I'm talking about amblyopia, which is actually suppressing our visual performance. And now I'm talking on how suppression can enhance our visual performance. So these are like contrasting words, but I'll tell you how suppression can enhance your visual performance. So some of the properties of perception. So the properties of perception is seeing, recognizing, preparing action, and emotional responses. Now what happens? So when we see an object, so the stimulus is going in the eye, and then through the visual pathway, it goes to the brain, and from the brain, what happens is the brain interprets that information and sends back through the outflow of stimulus, and then based on that we make any emotional response. So this is the process that happens, although I'm talking it so easily, but it's a very complex process, and it takes a lot of it takes a lot of perception to happen within this visual system. Now what I'll be emphasizing on is the pathway that is actually taking the information to the brain and then sending the information back, and help us to make an informed decision of what exactly we will be reacting on. So let's consider a saccadic eye movement. So looking from the left to the right, obviously you're shifting your eyes in a quite rapid pace, right? Now what's happening here is, although you're shifting your eye in a quite rapid pace, the information that is being received by the brain is quite stable and clear. is it? So what happens here is there is a filtering of visual noise. So let's say in a daily life, we see a huge number of objects, in huge number of information is going in the brain, but the brain does not interpret all the information. The brain only interprets the information that is essential and that is relevant for us based on our memory and based on the stimulus that has been given. Okay, now this inflow is called as proprioception, and the outflow, when the image, when the stimulus is going to the brain, and then when we are reacting to it, this outflow of information is called as the corollary discharge, which is the extra retinal, which is beyond the retina. These things are taking place. Okay. Now, visual suppression, to start with, so our visual world contains a vast number of objects, as I told very early in my presentation. And obviously, there are different location in three-dimensional space. Now, what happens is, to view an object, we need to initiate eye movements. So the eye movements are mainly the saccades, vergence, and accommodation, which are important here to actually receive the information. So this eye movements actually plays integral part. I know there are other eye movements like pursuits as well, but we will be emphasizing more on the saccades, vergence, and accommodation, and how they play an integral part in helping to perceive clear and stable image without any distortion. Let's say take an example of a camera. So if you are in a moving vehicle, or let's say in a train, and you hold the camera, the image that will be captured will be distorted. Similarly, if you now compare that with the human camera, which is the eye, what happens is whatever you're seeing is clear image, isn't it? So what is happening here is the image that we perceive is being clear. So there is always a positive factor when it comes to comparing between a camera and a human eye. So obviously we are blessed with such a vital and essential organ, which helps us to perceive clear world that we perceive in our daily life. Now, I've kept this poster for today's talk just to give you a real life experience. So let's do a practice here, and let me give you an explanation on how the image we perceive is relevant and how our brain eliminates all the irrelevant information. Okay, so I will be presenting two stimuli here. So one is stimuli A and one is stimuli B. So what I will ask you to do is look to stimuli A first and then move your fixation to stimuli B. Okay, so once you have done that, then I will be coming and talking on more of what has happened in between this eye movement initiation, that actually the change of the stimuli and what you have perceived and what our brain has actually eliminated, which informations are eliminated. Now I'll be presenting the first stimulus, which is stimulus A. So if I ask you to look at stimulus A, or you can try, if you're in a room, you can try on the left-hand side corner of your room. So fixate on the left-hand side corner of your room, or just fixate on the A on the screen. And then when I present the second stimulus, which is B, you change your fixation to B, and let's see what happens. So I'll be presenting the next stimulus, B. Now you can change your fixation from, if you're in a room, if you're taking that example, then move your fixation from one corner of the room to the other corner of the room. Now, when you have initiated this eye movement, what has happened is your eye actually captured all the information in between A and B. Similarly, if you're in a room, from the left corner to the right corner, whatever object is there, your eye actually captures all these objects. But our brain actually filters this out. It eliminates it. So the reason why it does is because the information that is in between is called as visual noise, which is unnecessary information, because the stimulus is given as stimulus A and stimulus B, right? Now, so this is something amazing, that our brain filters out any irrelevant information. Assume that you have been capturing all this information, irrelevant information. I've given you to see from A to B, and you're reading Mero, iTalks, session 125, webinar, all these things in between. So what will happen? It will create a visual noise, which is not necessary. Therefore, your reaction will be quite delayed. We will be quite puzzled, or we won't be able to give a better visual performance if our brain is actually capturing everything. So I hope that this explains how the suppression actually helps in real life performance. Okay, so like I said, the degraded information is removed from the awareness through this saccadic vergence and accommodation suppression. Now, to initiate from A to B, you are obviously initiating a saccadic eye movement. To fixate to from A to B, you're obviously initiating a vergence eye movement, because you need to converge to fixate at B, and obviously to make that B clear, you need to accommodate. So obviously, these are the three important eye movements that are taking place, and how these eye movements um, play an integral role in the suppression mechanism, because we understand that saccades are quite fast eye movements, accommodation is quite slow, although accommodation is not a pure eye movement, but still accommodation is actually, there is a ciliary muscle which keeps on changing. So therefore it is considered to be as an eye movement. And also vergence comes in between the pace of saccade and accommodation. Now, I talked about the visual stability and the retinal displacement during eye movements. So, I gave an example initially that when you are in a, like, let's say in a moving vehicle, so anything you see is perceived clearly. Otherwise, we won't be able to drive or walk in the street, isn't it? So all this interrupted, like the stability can be interrupted by the retinal displacement during eye movement. So for example, if someone is having poor eye movement, so they might not be able to filter out this information clearly. So that could be one of the major challenge to perceive a clear image. So eye movements definitely play an integral role here. But apart from that, there are two other things. One is the retinal function. So your retina should be healthy enough to capture the information, and which is still the retinal zone, and then send that information through the signal transduction pathway, through the visual pathway to the brain. And if that transduction between the electrical impulse to light impulse, and again back to light impulse to electrical impulse, this efferent and efferent pathway actually helps us in maintaining this stability. So like I said, so the first one is the oculomotor movements, and the second one is the retinal function, and third one is obviously the visual pathway that is also playing an integral role. So if there is any lesions in the visual pathway, or if there is any suppression in the pathway of the visual system, then obviously there will be challenges in perceiving a clear image. Now, to prevent these interruptions, what neurons do is it obviously it shifts the receptive fields in the in the parietal cortex to be prepared for the saccades to occur. So before you even initiate a saccadic eye movement to look from one point to the other point, your brain actually prepares within few milliseconds. Your brain prepares yourself, so how you need to initiate the eye movement. So let's say if you should look from left to right or right to left, or if, let's say, considering a vertical eye movement from top to bottom or from bottom to top. So this is something that actually needs to be this stimulus needs to come from the brain, and so that you can perform as soon as the task has been given to you. Now, the neural pathways that are essential here are the magnocellular and the parvocellular pathway, although coniocellular is another neural pathway. But because we are talking about the eye movements and mainly the saccades, vergence, and accommodation, based on the previous research, it has been found that the magnocellular and the parvocellular pathway is responsible for the saccades and saccades, vergence, and accommodation. Now, not necessarily magnocellular pathway is responsible for all of them, and not necessarily parvocellular pathway is responsible for all the three eye movements. Now, they are confined to their own specifications. Now, I'll come to the specifications. So magnocellular pathway, so these are the three important points that the magnocellular pathway actually possesses. Now, they have large receptive fields. They respond well to the transient dynamic movements, which is in terms of the visual stimuli, wherever the visual stimuli is presented, and the preference of low spatial frequency and sensitivity to the luminance contrast. So contrast sensitivity again plays an important role. So if I talk in layman, I understand that there might be quite heavy words here, but what I'll try to do is I'll break it down and explain as simple as possible. So let's say the magnocellular pathway here is responsible for uh, faster eye movements or the dynamic eye movements, which are considered like saccade is one of the dynamic eye movements, and obviously vergence is again a dynamic eye movement. But accommodation comparatively is not a dynamic eye movement. Okay. And the third point, what it says is it is more specified to low spatial frequency information. Now, this magnocellular pathway's preference for low spatial frequency information and sensitivity to luminous contrast is essential, or is the prime focus here. Okay. Now, if I compare with the parvocellular pathway here, what it says, it projects the upper dorsal layers of the lateral geniculate nucleus. Okay. Now, coming to the next point, numerous and have smaller receptive fields than magnocellular pathway. So what we have seen in magnocellular pathway, it has got larger receptive fields, therefore it can capture dynamic eye movements like saccades. But here it is very small. So because of its smaller in nature of the receptive fields, what it does is for the good processing of fine spatial information and color detection, like accommodation. Accommodation, what you need to do is you are confining yourself on a particular stimuli. It can be a word, it can be an object. So it is very confined, and it's that's why it's called as the fine spatial information processing. So that's why parvocellular pathway the uh, is responsible for the accommodative response here. Now, the other thing that I wanted to highlight here is the other thing that it says, it has got numerous and have smaller receptive fields because of its smaller receptive field nature. What it does is here it is actually picking up small details, and therefore it is more sensitive to higher spatial frequency. Okay, because to perceive a fine spatial information, you need to be acting on a higher spatial frequency. So contrast grating plays a very important part here in both magnocellular and the parvocellular pathway, considering the three different eye movements. Now, what is an average eye movement? So an average eye movement, if we see, let's compare between saccades and vergence and a combination of saccades and vergence. As you can see on the left-hand vertical bar, it says the time in milliseconds. So when a saccadic stimuli has been given, the eye starts, the onset latency of this movement is being measured in, the amplitude is measured in degree, as you can see on the right-hand side. Now, what it says here is the saccades only, which is, if you can follow the cursor, the saccades only here is around 150 milliseconds. Okay, it's only a saccade only stimulus. However, if we compare that with the saccade combined with vergence, you can see it is quite delayed. So it goes from 150 to, let's say, 175 millisecond. Okay. Now, if we compare that with vergence combination with saccades, then it is even delayed. So therefore, and this is the data from my PhD. So I have investigated this with the help of eye tracking system, like a video eye tracking system, and also analyzed the data in MATLAB, and therefore came up with this graph, which actually projects that how quickly the onset latency can be in different eye movement conditions. So what we found here is that, again, if I repeat this, so saccades are faster acting. Obviously, when saccade is combined with vergence, it becomes slightly delayed, and when vergence is combined with saccades, it gets even delayed. So saccades are faster than vergence in comparison. Okay. Now, coming to the contrast gratings, as I said, this is very essential in terms of contrast grating. So low spatial frequency and high spatial frequency. This is how a low spatial and high spatial frequency grating looks like. If you remember, I mentioned that magnocellular pathway responds more to the low spatial frequency, whereas the parvocellular pathway, which is the high spatial frequency. So this is how the grating patterns look like. And I will be giving you some examples from my PhD work as well, which is one of the chapters which investigated the suppression in different eye movements. And I'll be talking more on that. But before I go into detail, I wanted to talk about the visual suppression during saccades. So saccades can be mainly of two types, which is the horizontal saccade and the vertical saccade. Now, most of the studies that has been done was emphasizing more on the horizontal saccade because it's quite common. Even I gave you an example to look from right to left, not from top to bottom. So there is no vertical initiation there. But this was been overlooked, which I addressed in my PhD, and I was the first to look into the vertical saccades to see what suppression mechanism actually occurs in vertical saccades. Now, you might ask that what is the difference between horizontal saccade and vertical saccade? Both are saccades, both are same eye movements. Here, if you ask this question, it is obviously a good question to ask. But let me tell you, the involvement of eye muscles in horizontal saccade and vertical saccades are different. And as you already know, I'm assuming that that you know that the horizontal and the vertical eye movements differ not only in the extraocular muscles, but also the cranial nerves that actually sends the signal for this initiation. So because of having different extraocular muscles, different cranial nerves are also involved. Therefore, there is a difference between horizontal and vertical saccades because of its difference in the involvement of the difference of the involvement of extraocular muscles and the neural response to it, like the cranial nerve response to it. Okay. There is another saccade called as diagonal saccade, but this is not majorly practiced. We never record this much, but it still exists. Let's say if you're looking from the superior temporal to the inferior nasal, obviously you're making a faster eye movement diagonally, which is considered as saccades, but it is not being practiced quite frequently and also not in our daily life. So I won't be touching that much. So here we now know that not only horizontal saccades are mainly due to the magnocellular response, but also the vertical saccades plays the same. Although there is a difference between the extraocular muscles and also the different cranial nerves associated to it, but still the magnocellular pathway, because of its nature of the movement, the magnocellular pathway is also responsible for the vertical saccades. I'll show you some graph to actually demonstrate how the suppression takes place. So the visual suppression during saccades, and when I'm talking about saccades here, this is the vertical saccades, and this is from my PhD finding, that the suppression actually occurs near -50. As you can see that there is a drop here to contrast sensitivity of low spatial frequency. Okay, so the solid dot, the solid line here uh, is the static response. The dotted lines are, as you can see, the dotted lines on the top and the bottom, both are the confidence interval, the 95% confidence interval. And here are the different stimulus. If you follow the cursor, here are the different stimulus presented at the low spatial frequency. So that's low spatial frequency is 0.5 cycles per degree. And let me tell you, the high spatial frequency in this study was 9 cycles per degree. So the mid frequency will be somewhere around 4.5 or 5 cycles per degree. Okay. Now, when does the onset start? The onset actually starts quite early, but the suppression actually, so the stimulus has been presented here at 0, but the initiation of the eye movement, based on the contrast grating pattern, here, as we can see, the suppression drops here. These are the 3 key significant points where the suppression was actually measured significant, which was 0.2, 3, and 4. And this is the peak time when the suppression actually happened during vertical saccades. Now it will be ranging between -50 to +50 milliseconds. So the suppression, the onset latency of this is between -50 to 50 milliseconds. Okay. Now let's see what happens in vergence, because we discussed that vergence and saccades have the same. The magnocellular pathway is also responsible for both the eye movements based on the previous research data. Now here, as you can see, that the suppression that is occurring in vergence is slightly delayed. Now, and we can assume why it is slightly delayed. It's just because of its late response. If you remember the graph that we talked earlier, the bar chart, which showed that vergence was slightly delayed than saccades. So here um, that actually clarifies that statement that I presented earlier, that the suppression is also quite delayed, but not a very significant delay. So if it was 50 in saccades, minus 50 in saccades, here is minus 75 in saccades. Okay, and it ranges up to, sorry, minus 25, and it ranges up to, uh, sorry, I'll just correct it. It's minus 75, and it ranges up to positive 75. So this is the peak suppression point that takes place during the initiation, the onset latency of the eye movement. And obviously this is measured in milliseconds. So it all happens in milliseconds. It's a very quick process. We don't even realize what's happening, but this is what happens in the brain, how quickly the information is suppressed based on the contrast grating pattern. And therefore we can come into a conclusion that obviously the magnocellular pathway might be responsible for the suppression mechanism during saccades and vergence. Okay, now we have talked about saccades and vergence quite a lot, but now let me take you to accommodation. Now, what happens during accommodation? Accommodation is not a very fast process. It is quite a slow process. Okay, accommodation, basically what happens is it is quite delayed. So it starts, you can see the first point here. If you follow the cursor, you can see the first point, which is nearly 150 milliseconds, which is close to 200 milliseconds. And then it ranges up to 600 milliseconds. But the peak is noticed here in this middle 3 points. If you can see the velocity here, and also the amplitude of accommodation is measured here in the points in 1, 2, and 3. So it is quite delayed when compared to the saccade and vergence, because I'll just repeat that saccades and vergence was somewhere between minus 50 to 75. Here it is after the initiation of the eye movement that the accommodation takes place. Okay. Now, the visual suppression during combined eye movements. So we talked about individual eye movements, saccades, vergence. We have talked about the combination of saccadic and vergence response. But now let's talk about saccades, vergence, and accommodation. Because in real life, even if you consider the first exercise that I have given to do, like looking from one point to the other, like say from point A to point B, to look at from point A to point B, you are actually looking into both the stimulus. So you're initiating a saccadic eye movement. You're focusing on B. So you're actually confining your vision to B. So you're initiating a vergence response there. And also to understand that that is B, you have to have a clear focus on that. So the accommodation plays an integral role. So it is majorly seen in our reading activities or in our daily activities when we need to shift our eyes from one point to the other. I think it is very important that it is very important to know how the suppression actually takes place throughout this process. Okay. Now, as you can see here, when measured in combined, we can see that the saccades, which is the blue line here, the vergence, which is the brown line here, and accommodation, which is the green line here. So the saccades and vergence, if you can follow the time in millisecond, which is very close to each other. The saccadic and vergence response was quite close to each other. However, if you can see the accommodation, it is quite slow. The saccadic peak was very fast because of its dynamic in nature. Okay, but the vergence was again a bit lower in terms of the peak it goes when compared to saccades. But for accommodation, it actually starts quite delayed. There is quite a lag here. It is not a very steep slope, as you can see. Okay, so it is quite a lag here, and then it goes to the peak, which is very similar to the saccadic response, which is nearly 3 diopters here, as you can see, and then it stays quite stable throughout. So the saccadic response is going quite fast, and obviously it drops quite fast because of the stimuli, but the accommodation response will actually be consistent for a longer period of time when compared to saccades and vergence, because vergence is even low when we compare with accommodation and saccades, right? Now, what happens? So I obviously talked about the saccade and vergence, which is the magnocellular pathway, which is actually responsible here, that we can assume based on the data that we found here. So why do I say that? Because obviously it responds well to the transient and dynamic moving visual stimuli. So because if you remember, we talked about its large receptive cells and it's dynamic in nature, which can capture more information and can process faster information. That's why saccades and vergence uh, are considered to be because of the magnocellular response here. However, the parvocellular, which is for fine spatial information, and therefore we know that for accommodation we need to have a fine we need to actually look into the fine information to have able to focus and give a clear retinal image. Therefore parvocellular pathway is considered for the accommodation response because of its nature. So this is what we can actually say what's happening between saccades and accommodation based on the nature of the speed and obviously the nature of the reaction of this kind of eye movements. So what we have discussed so far, although I can go on for ages talking about of the visual suppression mechanism, but I think this is quite a complex topic. I mean, I don't know how well aware we all are in terms of the suppression that is taking place in our eyes, although we know that suppression in amblyopia. But this suppression is how it is enhancing our vision. And I hope that I was being able to clear that what visual suppression actually is, what are the neural pathways that are associated with different suppression mechanism, the eye movements that are associated, that are playing an integral part for this suppression. Obviously, the suppression mechanism during eye movements in singular or in combined eye movements. And also I give some real life examples um, of this suppression mechanism. So if you have any questions, I would like to take any questions and feel free to ask whatever questions you might have. I will be very happy to answer them. Thank you.
So thank you so much, Abhishek, for such a wonderful session. So we'll be heading out to our discussion session for taking up the questions if we have any. So are you ready to take the questions?
Yeah, sure.
So yeah. So may we have the questions displayed on our chat screen? So we will be displaying our each questions on the chat screen. So our first question goes like this. So I have a confusion regarding the amblyopic eye and eye movement. So does it relate? So does it relate to each other? If yes, how it can influence on the amblyopia treatment?
Okay. So obviously there is a relation here. The relation is purely based on the visual pathway here, because obviously amblyopia, we know that there is a suppression in the visual information at somewhere in the extraretinal area, although no such study has came to a fine conclusion of what exactly is the cause. But assuming that it is in the extraretinal area, which I talked about, the proprioception and then the corollary discharge. So if anything is taking place there, obviously that any deformity is taking place there, obviously it is causing amblyopia. Now the amblyopic suppression is what is doing is it is actually causing the eye to not work, which is called as a lazy eye. But here the suppression is in contrast. The suppression is happening in a hierarchy. So it is happening in the brain, where the information is being the irrelevant information is being moved out from the brain. Therefore, we can see and perceive clear vision. So the amblyopic eye, if you want me to compare, so the amblyopia is more of like a blocking of information, but here it is more of enhancing the information due to the suppression that is taking place. Although the suppression is quite different, but it has some relation. If you have asked in terms of the relation, I think that's the answer. Am I able to answer your question?
Yes, doctor, I hope that answers the question. So I can't see any more questions till now. So we'll be waiting for some few more minutes if any of our participants would come up with the questions. So before that, I want to do a short announcement here on our program. The announcement is that we are going to conduct a myopia symposium on 3rd July from the speakers directly from the Brain Holden Vision Institute, which is organized by Mirwai Foundation. So I request you all to sign up for this program and tune in to know more about the myopia and what's going all over the world. So that's all. And also we are going to launch our telemedicine as soon as possible. So we'll update it on our Facebook page. So stay tuned for that also. So yeah. So if you have any queries, then please come up with your questions. We'll be waiting for few more minutes. So Dr. Abhishek, I guess that's all were the questions that we had till now. And I hope our participants got enough knowledge from the today's talk and get the insights that they learned here today to impart in their future also. So with this, we are to the today's end. And before wrap up, I request you to share your few words to our program.
So first, regarding the questions, obviously, I understand that it might not be easy to come up with a question so quickly. As I mentioned very earlier, that it is this topic is it's not very commonly practiced, and obviously, it is not like contact lens or binocular vision in general. It's more of to do with the brain, so it comes in the neuroscience perspective, but it is quite essential. So in terms of the questions, if you have any questions, I'm happy to share my email address. You can reach out to me if you want further clarification. Whenever you might be able to process all this information and come with a question, I'm happy to answer them. So please reach out to me. And in terms of the initiation of MAROI, it's really a great initiation that giving such valuable information through these talks, having renowned people in this talk. So I really appreciate that, and I find that people might be quite lucky to be audience of MAROI. So that's it, and thank you very much again for inviting me for this session.
Thank you so much, Dr. Abhishek, for your kind words. And it's our honor to have you on this platform here this evening. So with this, we are to the today's end, and we'll be writing you with the questions if we have any in the future as well.
Yeah, sure. No problem. Okay. Thank you very much.
Thank you so much, Doctor. With this, I want to close the today's session, hoping to see you all again in the next one. Stay safe, stay connected. Thank you, everyone.